For thousands of years, people have looked into the night sky and asked the same question: what's really out there? Every generation believed it was getting closer to the answer. Ancient civilizations mapped the stars with nothing more than their eyes. Later, powerful telescopes revealed planets, galaxies, and entire clusters of stars. Then humanity launched observatories into space, hoping to see farther than ever before. But none of those missions prepared us for what happened when the James Webb Space Telescope opened its golden mirror and began looking into the deepest parts of the universe. Scientists expected Webb to confirm decades of theories. Instead, in several cases, it challenged them. The telescope has revealed galaxies that seem surprisingly mature for the early universe, planets that stretch current ideas of how worlds form, and details hidden inside distant cosmic structures that no telescope had ever seen before. Every new image has raised fresh questions. And in science, the biggest discoveries often begin with a simple sentence: "We didn't expect to find this." Today, we're taking a journey through some of James Webb's most remarkable discoveries. Because the universe isn't becoming simpler. The deeper we look, the stranger it becomes. When the James Webb Space Telescope launched in December 2021, the mission had one primary goal: look farther back in time than any telescope ever had. Unlike the Hubble Space Telescope, which mainly observes visible light, Webb is designed to detect infrared light. That difference changes everything. As light travels across the universe, space itself expands. During that incredibly long journey, the light stretches into longer wavelengths, eventually becoming infrared. To human eyes, that light is invisible. But to James Webb, it's exactly what the telescope was built to see. This allows Webb to observe objects whose light has been traveling for more than 13 billion years. In other words, every time Webb captures one of these ancient galaxies, it isn't simply taking a picture. It's looking into the past. Scientists hoped those observations would show how the first stars and galaxies slowly formed after the Big Bang. The expectation seems straightforward. The earliest galaxies should be tiny, irregular, and still growing. Instead, the first surprises arrived almost immediately. One of Webb's earliest deep-field images stunned researchers around the world. Hidden among countless distant objects were galaxies that appeared much brighter, larger, and more organized than many models had predicted. Some seem to exist only a few 100 million years after the beginning of the universe. That may sound like an incredibly long time, but on the scale of cosmic history, it's remarkably early. According to many existing models, galaxies during this period should still have been assembling themselves. Stars would have only recently begun to form. Large spiral systems similar to our own Milky Way weren't expected until much later. Yet Webb kept finding surprisingly massive galaxies. Did this mean the universe evolved faster than scientists believed? Or were astronomers misunderstanding what they were seeing? Those questions quickly became the center of intense scientific debate. Importantly, this did not mean the Big Bang had been disproved. Instead, it suggested that parts of our models describing how galaxies grow might need significant adjustments. That's how science works. New evidence doesn't end the conversation, it begins a better one. As researchers continued analyzing Webb's data, something interesting happened. The surprises didn't stop. Instead, they multiplied. Every observation seemed to reveal another object that challenged previous expectations. Some galaxies appeared to be producing stars at extraordinary rates. Others contained unexpectedly large amounts of dust. That may not sound dramatic at first, but dust is produced by earlier generations of stars. Finding large amounts of it so early in cosmic history suggests that stars were forming, living, and dying much faster than many astronomers expected. It's like opening a history book to the first chapter, only to discover an entire civilization already thriving. Scientists immediately began revising computer simulations. Some models were updated, others had to be completely reworked, and that's exactly why Webb is so valuable. Its purpose isn't to prove scientists right. Its purpose is to show what's actually there, even when the answer is unexpected. One discovery that captured worldwide attention wasn't a galaxy at all. It was a planet. Hundreds of light years from Earth, the James Webb Space Telescope studied an enormous exoplanet known as HIP 65426b. This world is unlike anything in our own solar system. It's several times more massive than Jupiter. It's extremely hot, and it orbits its young star at an enormous distance. Even more remarkable, Webb managed to capture direct images of the planet itself. That might sound ordinary, But imaging exoplanets directly is incredibly difficult. Normally, the overwhelming brightness of a star completely hides the planets around it. Imagine trying to photograph a tiny firefly flying beside a powerful searchlight. That's the challenge astronomers face. Using advanced instruments and specialized observing techniques, Webb succeeded where few telescopes could. For the first time, scientists examined the planet's atmosphere in remarkable detail. The telescope detected water vapor, carbon monoxide, evidence of complex atmospheric chemistry. Every new observation helps researchers understand how giant planets form and evolve. Yet HIP 65426b also raises important questions. How did such a massive planet end up so far away from its star? Was it born there? Did it migrate outward? Or did something unusual happen during the early stages of its system's formation? Scientists don't yet know. But every unanswered question becomes another target for future research. Then came another spectacular achievement. James Webb produced some of the clearest images ever taken of gravitational lensing. This phenomenon was predicted more than a century ago by Albert Einstein's theory of general relativity. Here's how it works. Mass bends space. When an extremely massive galaxy sits between Earth and another galaxy located much farther away, the foreground galaxy acts like a giant cosmic magnifying glass. Instead of traveling in straight lines, the background light curves around the massive object. From Earth, that bent light can appear as arcs or sometimes as nearly complete rings. These are known as Einstein rings. Some of Webb's observations revealed astonishingly detailed examples of this effect. The images weren't mysterious because gravitational lensing itself is unknown. Scientists understand the basic physics extremely well. What impressed astronomers was the extraordinary level of detail Webb could capture. Each ring wasn't simply beautiful. It became a scientific tool. By studying these distorted images, researchers can estimate how much matter exists inside distant galaxies, including matter that cannot be seen directly. This includes one of astronomy's greatest mysteries: dark matter. No one has ever photographed dark matter. It doesn't emit light. It doesn't reflect light. Yet its gravity appears to shape entire galaxies. Every gravitational lens observed by Webb gives scientists another opportunity to map this invisible component of the universe. In many ways, it's like seeing the outline of an invisible object by watching how it bends light passing behind it. We still don't know exactly what dark matter is. But James Webb is giving researchers one of their best opportunities yet to investigate it. Perhaps the most exciting part of Webb's mission isn't any single discovery. It's the pattern that's beginning to emerge. Again and again, the telescope is revealing a universe that is more active, more complicated, and more diverse than many scientists imagined. Every answer seems to produce two new questions. Every observation opens another mystery. And we're still only at the beginning. James Webb was designed to operate for many years. Its fuel reserves have lasted longer than originally expected. That means countless future observations are still ahead. Some may confirm current theories. Others may force scientists back to the drawing board once again. Either outcome is exciting, because the goal of science has never been to protect old ideas. The goal is to understand reality as accurately as possible. And if reality turns out to be stranger than we imagined, then our understanding must evolve with it. Another reason James Webb has generated so much excitement is that it isn't working alone. Every major discovery involves a network of observatories operating across different wavelengths of light, each contributing information the others cannot provide. Webb specializes in infrared light. Hubble primarily observes visible and ultraviolet wavelengths, while observatories like ALMA study radio waves emitted by cold gas and dust. Together, they create a far more complete picture of the universe than any single telescope could ever achieve. Think of it like assembling a complex puzzle. One telescope might reveal the stars inside a distant galaxy. Another traces the cold clouds where future stars are still forming. Webb excels at looking through dust that blocks visible light, exposing structures that older telescopes simply couldn't see clearly. By combining those observations, astronomers begin understanding not just what galaxies look like, but how they evolve over billions of years. That ability to peer through cosmic dust has transformed another area of astronomy as well: the study of stellar nurseries. Massive clouds of gas and dust scattered throughout the Milky Way are the birthplaces of new stars. In visible light, many of those regions appear almost completely opaque, hiding everything inside. Infrared light behaves differently. It passes through much of that dust, allowing Webb to reveal stars that were previously invisible. Those observations help answer fundamental questions about how stars actually form. Researchers can now observe young stellar systems while planets are still beginning to assemble from rotating disks of gas and dust. Instead of reconstructing planetary formation through computer simulations alone, astronomers are increasingly able to watch different stages of the process unfolding around real stars. That matters because our own solar system formed roughly 4.6 billion years ago, leaving very little direct evidence of its earliest history. By studying young planetary systems elsewhere in the galaxy, scientists effectively look back in time at conditions that may resemble those that once surrounded our own sun. Webb has also contributed significantly to the study of exoplanets, worlds orbiting stars beyond our solar system. Thousands of exoplanets have already been discovered over the past 3 decades. But finding a planet is only the beginning. The next challenge is understanding what those worlds are actually like. When certain exoplanets pass in front of their parent stars, a tiny fraction of starlight filters through the planet's atmosphere before reaching Earth. Webb can analyze that light using spectroscopy, separating it into its individual wavelengths. Different gases absorb different wavelengths, allowing scientists to identify chemical signatures within those distant atmospheres. Already, Webb has detected molecules such as water vapor, carbon dioxide, methane, and carbon monoxide in several exoplanet atmospheres. None of these discoveries proves the existence of life. Those molecules can all form through entirely natural processes. But each measurement improves our understanding of how planetary atmospheres evolve under different conditions throughout the galaxy. That's an important distinction. Headlines sometimes suggest Webb is searching directly for aliens. In reality, the telescope is searching for chemistry. Understanding atmospheric chemistry comes first. Only after scientists fully understand normal planetary processes can they confidently recognize something genuinely unusual if it ever appears. The same careful approach applies throughout Webb's mission. Every extraordinary image released to the public represents months of planning, observation, calibration, and analysis before researchers reach scientific conclusions. The spectacular photographs capture public attention, but the real discoveries emerge from painstaking examination of the data hidden within every pixel. Another remarkable aspect of the mission is its location. James Webb operates around the second Lagrange point, commonly called L2, roughly 1.5 million kilometers from Earth. From there, the telescope maintains a stable position relative to both Earth and the Sun, allowing its enormous sunshield to keep the instruments permanently cold. That cooling is absolutely essential. Infrared telescopes detect heat, and even the telescope itself produces thermal radiation. Without its multi-layer sunshield, Webb would effectively blind itself with its own warmth. By blocking heat from the Sun, Earth, and Moon simultaneously, the observatory remains cold enough to detect incredibly faint infrared signals arriving from the distant universe. The engineering required to achieve that is almost as impressive as the science itself. Webb's segmented mirror unfolded flawlessly after launch. Its instruments were aligned with extraordinary precision, and its cooling systems performed even better than mission planners originally expected. Those engineering successes directly translate into longer operational life and more scientific opportunities. Every additional year of operation means thousands more observations. New galaxies will be identified. More exoplanets will have their atmospheres analyzed. Additional gravitational lenses will help refine maps of dark matter. Entirely new questions, impossible to anticipate today, will almost certainly emerge from future datasets. History suggests some of Webb's greatest discoveries haven't happened yet. Many revolutionary observatories produced their most important breakthroughs years after launch, often while investigating questions nobody originally intended them to answer. That's one of the defining characteristics of science. Better instruments rarely provide only better answers. They also reveal entirely new mysteries. Perhaps that's the most inspiring lesson James Webb offers. Every generation builds tools capable of seeing a little farther than the previous one. Each new instrument expands the frontier of human knowledge, not by replacing earlier discoveries, but by building upon them. Hubble transformed our view of the universe. Webb is extending that legacy into regions of space and time humanity has never explored before. So when people ask whether James Webb has stopped the world, the most accurate answer isn't that it overturned everything scientists believed. It's that it has begun revealing details of the universe with a clarity that was impossible only a few years ago. Some observations reinforce existing theories. Others challenge them. Both outcomes represent scientific progress. The universe hasn't changed because James Webb was launched. Our ability to observe it has. And sometimes, improving the way we look at reality is enough to transform the way we understand it. With years of observation still ahead, the telescope's greatest contribution may not be any single image or headline. It may be the entirely new questions future generations of astronomers will ask because James Webb showed them something nobody had ever seen before. There's another reason scientists remain so optimistic about Webb's future. Unlike many earlier space telescopes that focused on answering a handful of specific questions, James Webb was deliberately designed as a general-purpose observatory. That gives astronomers the flexibility to investigate entirely new mysteries as they emerge. If another unexpected interstellar object passes through the solar system, Webb can observe it. If a nearby supernova suddenly explodes, Webb can quickly be redirected to study it. If future surveys discover unusual galaxies or strange planetary systems, Webb has the capability to investigate them in extraordinary detail. That adaptability means the telescope isn't limited to today's scientific priorities. Some of its most important discoveries may involve questions researchers haven't even thought to ask yet. History repeatedly shows that powerful observatories often become famous for discoveries nobody predicted before launch. Hubble wasn't built specifically to measure dark energy, yet it played a crucial role in revealing the universe's accelerating expansion. So here's the question for you. What discovery do you think will change everything first? Ancient galaxies, mysterious exoplanets, dark matter, or something we've never even imagined? Let us know your thoughts in the comments below. We read every one of them. If you enjoyed this journey through the universe, don't forget to like the video, subscribe, and turn on notifications so you never miss our next deep dive into the biggest mysteries of space. Thanks for watching, and until next time, keep looking up, because the universe still has countless stories left to tell.